Hello everyone and welcome. My name is Michael Rothberg. I am a member of the YCRC or the Yale Center for Research Computing. Uh, this video is to guide users on how to run AI ML workflows on YCRC computing systems. This is part one, which will be focused on machine learning. So up at this point, before watching this video, you should hopefully be familiar with how the YCRC clusters operate. And that includes how to access the clusters, whether that's logging in or knowing which cluster you're on, how to submit jobs both interactively and via batch submissions, how to build mini-conda environments, and the different types of storage available to you as a user. You should also have some familiarity with basic Linux commands. You can learn all of this in our Introduction to HPC video, which you can find just by Googling YCRC Intro to HPC. We also host this as a training every year. So before we dive into running these workflows, it's best to first go over what AI/ML is. Well, AI/ML, or Artificial Intelligence Machine Learning, is defined as any computer program that performs some task and improves over time with experience. And if you consider what AI/ML represents, artificial intelligence has been around for actually decades, and that started with machine learning. As we became more advanced and more developed in our knowledge, deep learning was invented. And from there, generative AI has been invented, which is leading the charge with the GPTs on the internet and so on. And as far as this presentation, to form our foundation, we'll be focusing on that first tier of artificial intelligence, or machine learning. In the outline today, we'll come with a brief overview of each method in machine learning, and then we will initiate the methodology to actually run these protocols on our systems. That'll start with data, involving data preparation and data ratios, how to choose a model, the advantages and disadvantages of each, how to set it up to run the cluster, what libraries you should be using, what modules you should be loading to install those packages, what type of resources you should be using on the cluster, and what recommendations we provide and how to monitor them, what errors that commonly occur in these machine learning workflows and how you can validate them, and then finally how you can move them into production. Where hopefully you will, at the end of this presentation, you'll have a conceptual understanding of how machine learning works. You will have learned the process to running each of the above methods on Yale Research Computing hardware, and you'll understand how to manage your resources to ensure optimal progress in your own research. So let's go ahead and get started with machine learning. Here is a funny comic of a human teaching the machine learning programs what a boat is. So if we attempt to define AI/ML, where artificial intelligence are machines that attempt to mimic human intelligence, then machine learning can be defined. So if we attempt to define AI/ML in simple terms, where artificial intelligence is defined as machines that attempt to mimic human intelligence, then we can define machine learning as advanced algorithms that learn and adapt patterns in that first iteration of trying to mimic human intelligence. Where specifically machine learning enables computers to learn from data and make predictions or decisions without being explicitly programmed. Instead of following a fixed set of rules, machine learning models identify patterns in data and improve performance as they are exposed to more and more data. That means that this model improves as you train it. Essentially, it's learning from the data you're providing. So if we consider machine learning protocols, there's really two main directions you can take when developing your models, and that actually comes down to the type of data you have. If you have labeled data, then you'll be doing supervised machine learning. And if you have unlabeled data, you'll be doing unsupervised machine learning. Well, what does labeled and unlabeled mean? Well, let's consider that at a closer perspective. And let's start with unsupervised machine learning. So when you start a machine learning model, you need to have some type of input data. In this case, our input data is going to be these images of animals, or in this an example of which is a dog and a cat displayed here. Now what makes this unlabeled is that there's no clear proof, there's no clear answer to the model or a label that says that the picture on the left is a dog and the picture on the right is a cat. Instead, the machine learning model has to determine what is a dog and what is a cat on its own. So what this means is that you're now inputting unlabeled data. The machine learning model is going to determine its own conclusions based on the input provided by analyzing similarities, such as the size of the ears or the length of the tongue. So these images will get inputted into the model where that model learns from the data. And then once that model has trained, it's ready to run, at which point you can input all of your data to generate an output. Now conversely, with supervised machine learning, instead of just having the pictures, you also have a predefined output. In this case, we're telling the model, this is definitely a dog, this is definitely a cat. Now when the model trains, it can compare its output to the answers to give a potentially more accurate representation of the outputs. And the same process occurs. You input this labeled data into the model trains on it, it develops a model that can be run after enough training has occurred, at which point you can input new data or testing data to generate your outputs. So how exactly does this change your output? Well, if we continue to consider supervised learning, where we now have these conglomerations of input data of cats and dogs that have been labeled cat and dog, a model is then able to take a new image, say this slightly obscure animal. It goes into the model, aka this box, at which point the model creates so many outputs. These outputs include the likelihood of it being a dog, a cat, or something else. Now, because this is a supervised learning model, it will produce one output, which will be based on the highest probability, aka the dog. So in this case, it will output the dog. What's key about supervised machine learning is that it provides quantitative answers. Conversely, if we look at unsupervised learning, we now have all of these images, but they're not defined with labels. Instead, the model will try to separate this data based on features, such as how long the tail is or the pointy ears. In this case, we've created 3 clusters, images of dogs, images of cats, and images of others, or in this case, giraffes. With unsupervised learning, you get qualitative answers, but that's not necessarily a bad thing, and it can actually be used to help organize your data to create labels. Where one thing you can do here is use unsupervised learning to take seemingly random data that has no apparent pattern to you or your researchers and produce potential features that you can then apply to supervised models to create quantitative answers. So let's start that process. So how do we get into actually running these models and knowing what we want to do? So the very first thing we're going to focus on is data. When it comes down to data, this is going to be one of the most important steps. Whatever you put in will define what comes out. If you've never heard of the phrase garbage in, garbage out, this greatly applies to all AI MI models, where if you put in bad data, you're going to get bad results. So what does that mean? What is bad data? Well, bad data is data that has a number of different potential obstacles inside of it that needs cleaning. So if you want to put in good data into your model, assuming the data is correct and accurate as is, you need to eliminate things such as duplicates that can affect how the model changes. You need to remove data that's incomplete. Maybe it's only half an image and it's not clear enough for the model to learn from. You need to remove outliers. Maybe there is a number that is much, much larger than the other numbers. This can greatly skew your data or create bias. And then finally, you need to normalize your data. You need to ensure the data was created under your data was finally, you need to normalize data. You need to make sure the data was all collected under the same scale. Otherwise, you will create bias inside your data. Whether that means normalizing all of your numbers to between 0 and 1, or ensuring that all of your images are the same size, and so on. The other thing you have to do is define how your data is going to be divided. Now that we have this clean, sparkling data, we think, oh, great, we can run our model, but that's not the case. There's a multi-step process to ensuring your model is performing correctly. What that means is that we now need to split our model into what will be 3 different segments to ensure that our model is both trained, validated, and accurate. So what that means is that we're going to take the majority of our data and turn it into training data. This data is used to actually train the model, and this is where the majority of the computing resources is used. During this process, the model is taking the data you provided and learning from it and defining and creating its probabilities to define outputs. This usually is about 60 to 80% of your data, of your total data being used to develop the model. Your validation data is what you use while the model is running to ensure that the model is training properly. It's the equivalent of saying of having a person in a room where the model is someone hanging a picture on the wall and someone is standing behind them saying a little to the left, a little to the right. In this case, the validation method is telling the model how to shift its probabilities to better represent the results we're expecting. This portion of your data is about 10 to 20% of your total data that you have available. And then finally, you have your test data. This is what you run on, this is the data you use to test your model to ensure it's producing accurate outputs. If you have bad test results, that means you need to go back and do some more training or modify your data. And just like before, this is 10 to 20% of data. The key difference between validation and test is that validation is being used to help shift the answers the probabilities the machine learning model is generating. Your test data is used to actually prove the model is accurate. So you're not modifying the model. This test data, you're just saying, I put this data in and it should accurately determine what's a dog and what's a cat. If not, I need to go back and modify my training or validation protocols. So now that we have covered data, which again is the most important step that you'll be doing to create your models, we can move on to the next step, which is choosing what method you want to run to do your ML machine learning model process. So what are your options? Well, like before I said, there are two paths. You have supervised and unsupervised learning. Well, let's say that we have unlabeled data. Then we can do unsupervised machine learning, which uses methods like clustering. There's a number of methods here. I'm going to cover the two main ones, which is principal component analysis and clustering. Principal component analysis simplifies data by reducing potential variables or dimensions that affect conclusions. What this means is that let's say we have these pictures of animals again, and they have so many features. Let's talk thickness of fur, height of tails, length of nose, color of tongue. What PCA does is it looks at all of those images and determines what are the key values or dimensions that really affect the output of the model. So maybe if we're comparing cats and dogs, size of the ears, the shape of the ears is a key factor. So instead of having to focus on 10 different features, we're now just looking at the sharpness of the claws and the shape of the ears as our two main features. This greatly reduces the complexity of the data and allows us to find patterns. There's also clustering, which where data is grouped based on similarities, where if we consider maybe a chemical analysis, we'll see chemicals grouped by similar melting temperatures or similar structures, the number of carbon backbones, or the type of functional group on the end of those molecules. So we do have an example to run through how this kind of works. In this case, we have what is a generated set of false data where we have 40,000 tumors that are being compared, that have been tested, that contain 20,000 genes. Where the task is to recommend treatments based on apparent activity for 40,000 tumors. Since there are 20,000 genes per tumor, there are 20,000 possible dimensions or values for comparison, which is a near impossible task for a human researcher, to identify patterns from. So instead, we can use unsupervised learning to help simplify and identify patterns for analysis. So what we're going to do here is use principal component analysis to reduce dimensions to the most impactful characteristics. And then we'll use clustering to create similar groups for recommended treatments. So this is an example of a PCA generated graph in 2 dimensions, where I've reduced these 20,000 dimensions to the 2 main dimensions. What that means is I've now reduced all of the different factors that cause the toxicity of this tumor and reduced them to the 2 main factors that will help me determine the level of toxicity of these tumors. How this works is that the model essentially examines all of these patterns and determines the ones that are most likely to produce the desired output. Principal component 1, or the x-axis, represents the biggest factor in the data that contributed to the danger of the tumor. In this case, I've defined this as inflammation. Principal component 2 is now the second and most important factor, or the level of immune activity these tumors were causing inside the body. Now I should point out that when you do your principal component analysis, these aren't labeled. The computer has no idea what the actual proper term is for these key features, and it could be a combination of a couple features. What that means is that you as a researcher have to determine what that feature is if you need to define it. Just for this example, I've defined them for easier understanding. So now that we have our simplified PCA with our two dimensions, we can do clustering to examine how those dimensions affect the different results of our output. So in this case, my clustering created 3 clusters. The first cluster, which was defined, which has low inflammation and low immune activity, I determined were likely dormant tumors. Tumors that had inflammation but low immune activity were active tumors, but maybe weren't cancers. And then cluster 3, which had both high inflammation and high immune activity, were determined to be cancerous tumors based on the data provided to the model. What that means is that as a researcher, I can now take new data, say a new tumor that's inputted, and based on what group it's clustered into, we can create an immediate response to the patient to determine their next steps. Whether if they have a tumor in group 1, then we can tell them that they can wait and see and monitor. In group 2, maybe further testing should be done, and group 3 should move to chemo. What this has done is taken an incredibly complex set of data and reduced it to an understandable level of knowledge for the researcher or doctor or whoever is studying this to create recommendations for patients quickly with minimal testing, with minimal further testing. But and that is an example of minimal further testing. And that's an example of using unsupervised learning to create a functional model for analysis. But what if we have labeled data or predefined outcomes? Then we can use supervised machine learning, which has a number of options. You can use regression to predict patterns or classification to create categories or decision trees. So what are these options? Well, regression is used to predict values based on past experience. And an example I'm going to show here is that we're going to predict house prices based on the features such as the size or location of the house. Where if we input the house, the price, and their features, the model can create a regression. It doesn't have to be linear, but it will learn the relationship between different features. And then you can take a new house that hasn't been priced, input the features, and the model will attempt to predict the price or predict the features that cause that price. The type of regression can be changed to fit the data. Ideally, it's just polynomial, lasso, linear. There's a lot of flexibility in the type of regression you want to do, and it is important to test those as they do change your model's accuracy and can affect the final outputs. Classification is how you can use supervised machine learning to separate data into predefined categories. So let's say we have the images of cats and dogs, and we need to separate them into these features. So what the compute model once again learns the difference in features that defines a cat or a dog. And when you input a new image, it will then predict what group or category the new image fits into. In this case, it would have been grouped into a dog. In this case, it would have been grouped into a dog. So in summary, if you have no labeled output, no predefined outcomes, you need to use unsupervised learning. So you can use clustering to do customer segmentation or anomaly detection. If you need to reduce the complexity of your data because it has patterns but you can't identify them, you can use unsupervised learning or PCA to reduce the complexity of that data and identify key factors in the data's outputs. If you need to predict a specific number, regression is a great tool for predicting patterns such as temperatures or forecasting. If you need to predict a category or label such as defining something as spam or what disease or the danger of the disease, or to recognize an image, then you can use classification and supervised learning. So those are the different models, the main models you can choose from in machine learning. And once you know your data and you know what you're trying to solve, you can choose your model. And once you've chosen your model, you can move to setting it up on the YCRC computing clusters. So to do that, you need to make sure that you're on a compute node on our system. If you attempt to build models in the login node, it'll likely result in a failed installation of packages because we use these login nodes for logging in and they have tight restrictions to stop any kind of computing from occurring. So make sure you're on a computing node. To see how to do that, if you need a refresher, you can look at Intro to HPC or you can look on our YCRC doc pages. For machine learning, I recommend two programs for developing machine learning models, either Python with Miniconda or R. There aren't really significant disadvantages or advantages to either program. Both use multiple CPUs with minimal setup. It's really just user preference of what you're most comfortable with. There are other options such as Julia, C++, or MATLAB, but these programs aren't as well documented and can be a little harder to implement. So if you want to use the Python route, what you want to do is create a Conda environment in most cases. So you'll request a compute node like so. This will get you a compute node on our devel partition. You'll load the Miniconda module that we provide with module load Miniconda, and then you'll create your environment by doing conda create. You'll name your environment, install a version of Python. In this case, I've done 3.ask, which means it'll install the newest version of Python 3. And then I'm defining what kind of ML packages I want, such as like PyArrow or SciPy or so on. Once the environment is built, you activate the environment and you can run it using your Python commands. Here is a list of different Python packages you can use for machine learning in Python. Some common ones are scikit-learn, TensorFlow, XGBoost. For unsupervised learning, k-means is a very common one used in unsupervised learning. But you can go back and refer to these as you choose to create your machine learning models. Now, if you're doing R, it's a similar process. You again allocate a compute node. You can look at the different R versions. In this case, I wanted R 4.4, so I used module avail R to see all the different versions of R available in the cluster, and then I loaded 4.4. I then pre-installed any packages with install.packages command or devtools or bioconductor, and then I run my R script, whether that's in Open On Demand on the RStudio or on the terminal with R script commands. Again, just like with Python, we have a list of the number of packages you can use in R to do machine learning. Again, common ones, super common ones used is Keras, random forest if you're interested in decision trees. For unsupervised learning such as dimensionality reduction, UMAP is very, very common. But go ahead and refer to this as needed. These are common packages you can use in your machine learning protocols. So setting up the model, not so bad. It's mostly knowing what packages you want and then having your data cleaned. But what about what type of resources you want to use on the cluster? Deciding the type of resources you want to use can be kind of complex. There are CPUs, GPUs, different memories, number of CPUs. It can be a big decision and part of the researcher process. Because of that, we have a number of different recommendations that we can offer to run your machine learning workflows on our systems. So there are really two factors to consider. It's how much memory do you need, and do you need a CPU or a GPU? Well, when it comes to memory, it's actually pretty straightforward. You can take the size of your data set. So if you have a data set that's 10 gigabytes, you add a little bit of buffer, say another 5 gigabytes, and you request 15 gigabytes of memory from the cluster. Now I should be clear that it's not the size of your data set that you have it's the size of the data set once it's loaded into your program of choice. So if that's R or Python, you may see a different size requirement than say your compiled or your compressed data that you're using. R and Python can both inflate data size for various reasons, so you may have to play with that data a little bit to get it to load correctly. Now, when it comes to CPUs or GPUs, you want to use CPUs. Machine learning has been around for a number of decades now, and most packages that have been developed for machine learning are optimized for CPUs. They may be slower or inefficient on GPUs, except in extreme cases. And additionally, as a user, our clusters between the three of them have over 40,000 CPUs, but only a couple hundred GPUs. So realistically, if you can use CPUs, you'll be able to access those resources faster. And since GPUs aren't speeding up the actual analysis, most likely, you will experience a faster progression in your research by sticking to CPUs. And just because they've been compiled to build with CPUs, most of the packages that we listed before, if not all of them, can use multiple CPUs to accelerate that analysis. But still the question remains, how many CPUs should I use? And why should you as a researcher care? Why can't you just request, say, 60 CPUs every time and move on with your research without thinking about it? Well, there's a couple of reasons for that. And it all boils down to kind of one simple statement, which is keeping it simple. You don't want to overcomplicate the process you're doing. So let's say that we have what is your final project code, right? You have this project code, you put it together, you've put together different sessions, maybe it's a little chaotic, we're not professional developers, right? So we have essentially what is this hay bale of code of different pathing, different loops that we've now created. And what we're finding is that now there's some kind of error in it. There's kind of error that's causing it to not interact well with the cluster, and you're running into obstacles. Well, at this point in your code, at this final project point, trying to figure out why it's interacting with the cluster incorrectly can be like trying to find a needle in the haystack. It can be very time consuming. It can take a lot of effort to fix this one issue that's preventing progression on our resources. So instead, you want to try and keep it simple. What I mean by that is that if we actually have a project start, so we have started our project, to better convey what we're saying here. We've started our project and we have our initial sample code. We have started our model, we have this nice simple model. However, when we actually ran it on, say, 10 CPUs, it ran slower than we expected. Maybe it took a day, maybe it took a couple hours instead of 10 minutes. But it ran, it completed. So as a researcher, I've decided that that's good enough. I'm going to just continue developing my code and not worry about the speed. It's just slower than I expected. So my code develops and it's still running slow, maybe slower. Maybe now my code is taking days to run and I was expecting it to be a much shorter time frame. But I continue to move on because my code is working. Now I have my final project code, but it is slow as a snail. It is taking days, if not weeks, to complete a job. But at least it's running, right? My work will complete. Thankfully, because of HPC resources. However, you hit a limit. On our clusters, we have something called fair use limits. What they do is they enable fair use limits are limits imposed on groups or users to ensure equal and fair access to YCRC resources for all researchers. What this does is it prevents users from being able to monopolize all the resources on the clusters. We can't have one group request all 40,000 CPUs. And because everyone is forced to share the resources, we have to ensure they're shared fairly and everyone has an equal chance to use the resources when they need them. This also makes the wait times more consistent for users. There's a limit. There is no iterations or where there is a large group of power users taking over the cluster. The wait times are fairly consistent. This provides a consistent resource availability that allows researchers from all fields of research at Yale to access the resources. Why you hit this impactful at this point on your final code is that now you can't run the code as long as you need to because our limits won't let you run the resources for that length of a period of time without some kind of checkpointing involved. So the reasons we have partitions and fair share is so that we can determine partitions to run your research. So I'm highlighting Boucher, our newest cluster here, where if we look at our different partitions, which if you remember from Intro to HPC is different areas in the cluster you can request resources from to receive different benefits. So the develop partition, which I highlight first, actually has a limited number of CPUs in it, only 128 CPUs. I highlight this partition because it's kind of like your troubleshooting partition. If you want to run something interactively really quick, you want to test like 5 minutes of code, you hop on Devel with like 2 CPUs and you can run it. You can have a job running and test it. But you can only have one job running. This is really just a almost an introductory partition, so that users can log in, check out their code, and then move on to the actual power partitions. So the main partition of relevance in machine learning is the day partition. This is where 99% of jobs, just an estimate, but a high amount of jobs occur on our systems. And because of that, we provide it with the most CPUs. In a day partition on Boucher, there are over 5,000 CPUs available for use. In addition to that, you have over 24 hours. You can have up to 24 hours of runtime to complete a single job, and you can request up to 1,000 CPUs. So we have the majority of resources in our day partition. However, if say your research is slow, you have that walker pace or snail pace of your code, and your job can't complete in a day, then you're forced to use a week partition, which only has 384 CPUs in it, of which you can now run for 7 days, but there's much less resource availability. Or maybe you haven't optimized your data or cleaned your data enough, so you need more memory than is available on the day partition, which, to be clear, to not use a day partition, your data needs to be over a terabyte in most cases, unless you're on Grace and it's over 500 gigabytes. In Big Mem, and similar to Weak, you have a significantly lower number of CPUs, 156 CPUs on Big Mem for a 48-hour runtime. And again, the number of maximum CPUs you can use is greatly reduced. So on day, you can use 1,000 CPUs at one time, or are spread across many, many, many jobs, but you're limited to 128 or 64 on the week in Big Mem. So if you stick to day where there are more resources, more flexibility, and shorter runtimes, you will get faster access to resources, which means your project will complete faster. To put it another way, you know that every job running on day is going to finish in a day. So even if you're in the queue waiting for your job to start, you know that in under 24 hours, it is more than likely your job is going to start. If you're waiting in the week queue, and there's a queue of people waiting to wait, it could be over 7 days before your job even starts. So sticking to the day partition is really great for research progression. And this type of distribution is reflected in all of our clusters. In Grace, you see we have over 28,000 CPUs in day, but under 1,000 in both weak and Big Mem. The same thing occurs in McCleary, where we have 2,000 CPUs in McCleary and under 1,000 in weak and Big Mem. So again, the conclusion to take here is that if you can make your research faster, then you can have a faster project completion. So it's imperative to know that you're using your resources correctly. So what that means, if we then consider that big project and waiting for all the time you need on the week queue to find that you then have to go back and say, I need to regenerate my code, I need to fix this so it runs faster. You're now playing inside this giant haystack of code, and to fix this error could take you days, weeks to kind of identify the error and correct it. Because this could have been caused from not using multiple CPUs this whole time. Maybe this whole time you thought you were using 30 CPUs, but realistically you were only using one CPU, and that's why your job was running so slow. Now you need to go back and fix that in all of your code to understand what went wrong. Maybe your loops are labeled incorrectly or not operating correctly in such a way that they're looping more than they should, which is slowing you down. So alternatively, if there was a focus on resources in the start of the project, just like before, you have your initial segment of code, and it's slower than you thought. So you looked at your resources, which I'll get into in a second, and you said, hey, something's wrong here. Let me play this code and make it run to the speed I'm expecting it to run. And because of that, searching for that error on that much smaller segment of code, instead of taking days or weeks, takes maybe an hour or two, maybe a few minutes, maybe a few hours. But either way, it's much shorter than trying to fix an error in a larger segment of code. Because you're able to fix that error now, your code is suddenly fast. And as your code grows, it maintains that speed, and you're able to easily progress to project end without running into fair use limits or needing to use the longer wait time queues. So ultimately, if you can ensure your project is operating well at the start by using our resource monitoring software, which I'll show in the next slide, you'll be able to complete your research at a faster and more efficient rate. So how exactly do you monitor your resources? Well, that is a tool that we provide called Job Stats. So you can see more on Job Stats on Intro to HPC, but to access it Open On Demand, you click the Utilities menu on Open On Demand, click User Portal, and then Job Statistics. You can then enter a job ID to see the output, or you can enter it in a terminal by doing Job Stats, the job ID. If you use Open On Demand, you'll see graphs like these. This is a graph of a CPU job that we pulled from random that was using 2 CPUs. Now, the things to take note here is that if on this graph you're using 100% of the CPUs, that means you're using all the CPUs you requested. So in 2 CPUs, that means that 1 CPU represents 50% of the graph, and the total of those 2 CPUs makes 100%. So when you see the graph plateauing at 50%, that means only 1 CPU is used in that time. Now that's not necessarily a bad thing. If you have sometimes loading data only uses 1 CPU, there are going to be non-parallel processes in your workflow, so you wouldn't expect to use all the CPUs all the time. But if your job never breaches that line, say 3 CPUs or 4 CPUs, 33% or 25%, never breaches that line of 1 CPU, that implies that even though you're expecting parallelization, it's not occurring in your code, and you should need to go back and examine why that's occurring. So as I just said, that does translate. So no matter how many CPUs you have, you can determine the exact percentage of what you should be seeing on the graph. So if you have 5 CPUs at 20%, that means 1 CPU at 40%, 2 CPUs, and so on. So if you're never crossing that 20% threshold, then you are probably incorrectly parallelizing your code and you need to go examine the code and debug it. Job stats can also be used to monitor your memory and GPU usage if you're needed to. So you can see if you're implementing your GPU, you can see maybe you're requesting too much memory, or maybe you're like a little close to the memory that you're hitting and you're worried you might have out of memory limit. Then you can increase the memory or decrease it as needed. So what about the case where your model is as fast as it can be? Maybe it has limited parallelization because that's just what the code is. There's no way around it. But your model needs to run longer than what our fair use allows. Well, then you can use something called checkpointing, where if you've played video games, you might have seen checkpoints like the Super Mario flag in Super Nintendo, or the Sonic checkpoint in Sonic the Hedgehog. These are essentially save points. So if you have a model running, like say an 8-day job, you instead then you create checkpoints within this job that saves the outputs after so much time. So let's say after day 1, we have this saved output of all of our model training for that day. We then use that day 1 output to submit the next job to then produce our day 2 output. So we've now completed 2 days of training via 2 separate jobs. And this continues for the 8 days. 8 different submissions until we have our final training output on the 8th day. The great thing about checkpointing is that, once again, this is another way to avoid the weak queue or big mem queue, which can have longer wait times, and stick to the day partition, which means you can have faster access resources and a faster job completion with just a little more work on your end. This also protects you from the other side of using a computing system. Just like with your own computer, the HPC clusters can have things like node fails or power issues that cause the nodes to reboot and kill jobs. This is a very rare occurrence, but it does happen. If you have a longer running job, you're at a higher risk of that happening, just because that's a longer time in which that bad experience could occur. And then let's say that happens on day 6 of your 7-day job, you've lost 6 days of computation, so you now have to redo. If you had been doing checkpointing, you would have lost maybe just a few hours or 12 hours of that computing. So checkpointing in general is a good practice that you should be using for your models to ensure you're not wasting computing resources and not losing too much of your own research in the case of extreme environments. So that's how you control your resources in HPC. Use job stats to monitor it. use checkpointing to save your data points, and through that process, you can have a quick and efficient analysis using our HPC systems or on your own personal machine. The last thing you have to do when running machine learning models is check for errors. So when you have a machine learning model, ideally, in the end, you have essentially what is this balanced progression through your data, where it seems it somewhat follows the data, your line of regression perhaps, but it doesn't follow it explicitly. So you can have something called overfitting, which is when your data performs well during training, but not on validation or test data. What that means is that instead of following the smooth line through the data, it instead seems to be following each test data point. That means you've overfit your data. That means maybe you don't have enough training data, so the model is being very rigid. Or maybe there's too many features and you need to use PCA to simplify it. Maybe you use the wrong regression model and polynomial gave it too much flexibility, or your decision trees were way too thorough and need to be shorter or broader, so they're not being forced to fit the training data explicitly. The other side of the coin is underfitting, where the line doesn't seem to follow the data at all. This means that your model performs poorly in training and validation, and there's never a time where it does well. Maybe your model is not complex enough now. Maybe you need not linear but polynomial. Once again, it comes down to the data. So you can see a trend. Data is the most important step. You need to increase the amount of data. Maybe you haven't trained it enough. Maybe it ran for an hour and trained on the data twice, but it needs to train maybe a magnitude more, and then you'll have a better fitting model. There's a whole bunch of steps that you can take, but these are common issues that will occur. Now, for cluster-specific errors, they're almost going to be entirely out-of-memory errors in the case of machine learning or missing libraries. In the case of out-of-memory, if you are on RStudio and it freezes and then crashes, it's almost definitely an out-of-memory error. You could check it by doing job stats to job ID, but if it freezes and crashes, you could also just increase your memory and it'll probably work. Python, a little more explicit. It'll give you an OOM error, which stands for out of memory. Just like with RStudio, you increase that session memory request and you probably won't have that issue. Let's say that you log on to Open On Demand today and suddenly you can't access any apps, any kind of interactive software. Your home quota is probably full. You need to move your data to your project, your Scratch, or your PI storage. You can run get quota to confirm that. If it's something Conda related, we at the YCRC can help you fix that. We have a protocol to move environments and so on. But if OOD is not working properly, check your quota and then move data if you need or contact us. So those are the common errors that you can have in machine learning. And throughout that process, once you get here, you can move this model into production because you now have a trained model that ran on the resources efficiently in such a way that your project was completed in a reasonable amount of time. You checked for your errors so your model is not overfitting or underfitting, and now you can use the actual data you want to analyze to produce results for your research. So in summary, your most important step in machine learning and really this whole AI ML series will be data preparation. If you put garbage in, garbage will come out. So make sure you're removing duplicates, normalizing your data, removing incomplete data, and so on. If you're doing supervised learning, you need labeled data. That means you need the data to have predefined outputs. If you don't know what those predefined outcomes are, or the data is too complex to find a pattern, you can use unsupervised learning to reduce the dimensionality to simplify the pattern identification for you. As far as using machine learning on the cluster, we recommend Python and R. Both have their advantages and disadvantages. You can also use other programs like Julia or MATLAB, but Python and R are the best well documented for machine learning workflows. Be aware of partitions. There are much more resources in day than week or big map. So if you can stick to the day partition, you'll have quicker job starts, which will lead to quicker research completions. You can optimize that by ensuring using multiple CPUs or by employing checkpointing into your workflows. And then finally, keep things simple. It's a lot easier to simplify a small segment of code than it is to wait till the end of the project to realize there's some error or parallelization issue, and then trying to troubleshoot that issue when you're looking at thousands of lines of code. Instead of a few hours, you're looking at days and weeks of troubleshooting. So make sure your initial code is running well and running correctly as you expect, and then from there, it's a lot easier to ramp up and have a producible result for your own research. And of course, the Yale Center for Research Computing is always here to help. If you have questions about your machine learning workflow, installing a package, you need a program installed on the cluster, or you just want to talk about your workflow and how you could accelerate it, we're more than happy to help. You can contact us at research.computing@yale.edu. We also have our docs page that you can access at research.computing.yale.edu. This provides information on how to run common programs, how to use Jupyter Notebook, our user's guide at docs.ycrc.yale.edu provides this information as well. We have office hours that you can come at 11 a.m. to noon to talk about simple questions like building a content environment. If you have more complex questions or need a longer consult, we are always available to consult any day of the week. You just need to send a request to research.computing@yale.edu. And then finally, just like where this video is, we have a YouTube channel for all the different videos, including part 2, which will be on neural networks. So I hope you found this video helpful, and I look forward to hearing about your research on the cluster.